Welcome back everyone. In this lesson we will learn about another open method which is named as Secant method. It is similar to the Newton-Raphson method, but it's a slight modification of the previous one, and in this lesson we will learn about the details of the Secant method. As we learned in the previous lesson that the Newton-Raphson formula looked similar to equation 1, something like this: xi plus 1 equal to xi minus f of xi divided by its differential. The denominator term, the differential term, is the slope of the function. It's the first order differential form, and it can be determined either analytically or using backward, forward or central divided difference formula. So we already know that in the from the previous lesson. So the value of the backward divided difference formula of the denominator, which is f prime of xi, can be expressed in the form of equation 2. So if we substitute equation 2 into equation 1, then the formula becomes something like this, which is equation 3. So this equation 3 is our second formula. So if you notice that this second formula is completely a numerical method, numerical formula. So because in the Newton-Raphson method we have seen that in some cases we determined the differential term analytically, but here in second method we have determined the differential term using numerical formula like backward difference formula, and then substituted this into the main equation. So equation 3 is completely a numerical formula. The equation 3 in the previous slide, that means the second formula, is also known as the linear interpolation method. The reason behind this terminology is something like this. Look at the figure. In the figure we are seeing a function that is drawn with respect to the independent variable x. And in this Newton-Raphson method, what we did, we assumed an initial point, suppose xi, and at that point of xi, we calculate the function value f of xi, and then we draw a tangent line to the function which intersects the x-axis at a next point xi plus 1, which is the root approximation. But in case of second method, what we do, we initialize two different we initialize with two different points xi and xi plus 1, and then we draw a second line, an intersection line through the function which intersects the x-axis at a specific point. So what does it mean? In the Newton-Raphson method we drew a tangent line, but now we are drawing a second line. So that's the difference between the Newton-Raphson and the second formula. So if we want to derive the second formula, we can derive it something like the way we did it in the previous slide, or we can easily derive it from the using the slope equation that we did in the Newton-Raphson method. The algorithm of the second method is pretty straightforward. We initialize the method with two initial guesses, xi and xi minus 1, and then we apply the second formula, which is something like this in step 2, xi plus 1 equal to xi minus this term, and this is our second formula. And xi plus 1 is the root approximation of the current iteration, and then we calculate the relative percentage error using this formula with the help of the approximation of the root from the current iteration and from the previous iteration. So if this error is less than the predefined stated value, then we terminate the calculation. Otherwise we go to the step 2 and repeat the calculation. So this algorithm is very straightforward. So remember one thing, although in second method we are using two initial guesses, this is not a bracketing method, because in the bracketing method we ensure that there is at least one root which is between the boundary points. But in the case of second method, there is no such condition. That means it is not necessary that there should be a root between the two initial guesses. So that's why second method is not a bracketing method, rather it's an open method. So let's look at an example using the second method, which is f of x equal to the power minus x minus x. So this is our function, and the initial guesses are x naught equal to 1 and x minus 1 equal to 0. So using these two guesses and the second formula, we can find the root. So let's see how we can do that. The solution process is very much similar to the Newton-Raphson method. If you remember, we showed the same function in the previous lesson in the Newton-Raphson formula. So if the process is to be repeated, it's not actually time worthy. So if you want to calculate the root of the function, you can proceed in the same way that we did in Newton-Raphson method. So only the formula are different. In the previous lesson we used the Newton-Raphson formula, but now we will be using the second formula. So the calculations are very much similar. So one thing you should remember that although second method is an open method like a Newton-Raphson method, but second method, whenever it converges, it usually does that at a quicker rate than the false position method and other bracketing method. So Newton-Raphson method and second method are both more favorable than the bracketing method. Now we are going to look at a different version of the second method, which is a modified second method. If you remember from the slide number 2, there we derived the second method by substituting the differential term into equation 1, and that differential term was determined using the backward dividend difference formula. But there is an alternative to this version. We can use a fractional perturbation form which can be substituted in equation 1. So what we do, we approximate the differential term something like this: equation 4, f prime of xi equal to f of xi plus delta xi minus f of xi divided by delta xi. So what is this term delta? Delta is a small perturbation function. It's a small value. So what does it do? This equation 4, it calculates the differential term with a small step value because of the delta. So once we substitute this equation 4 into equation 1, we get a different second formula, something like this, like equation 5. This equation is also a second formula, but a modified one. In the last case, normal second method, we had to use two different initial starting point. But in this case, look at this, in the right hand side of equation 5, we need just one initial point. That means xi. So that is the difference between the modified second method and the normal original second method. In the original case, we needed two different starting point, but now we need a single starting point. So that's how the second method can be modified, which is something more like an open method. So let's look at an example using the modified second method. So we have a function which is f of x equal to e to the power minus x, and we have an initial starting point of x not equal to 1, and we have a delta value which is 0.01. Also we are given the true root, which is 0.5671439. So this is for the purpose of comparison, and once we do that, we can determine at which point we need to terminate the code. So let's find out the solution. So we have at iteration 1, we have the initial point x naught equal to 1. So we find out the value f of x naught, which is minus 0.63212. Then we calculate x naught plus delta x naught and its corresponding function value, and next we substitute all of these values into the modified second formula, and then we can find the approximation of the root. So in this case, we have found the root to be 0.53763, and since we are given the true root, So we need to use the formula of true percentage relative error. So if we were not given the true root, we would have to use the approximate relative percentage error epsilon a. But since we are given the true root, we are using epsilon t. So the error turns out to be only 5.3%, which is pretty much low. So let's move on to the next iteration. In iteration 2, we are now getting the new approximation of the starting point, which is 0.53763. We derived it from the iteration 1, and then we calculate f of x naught plus delta x naught and its corresponding function value, and we substitute all of these values into the modified secant formula, and we will get our new approximation of the root, which is 0.56701. So in iteration 2, the true percentage relative error turns out to be 0.0236%, which is very much lower than the first iteration. So if we want to go further, we will have a more precise result. For example, at iteration 3, we are having an error which is very, very low, 2.365 of the order of minus 5. So once we do that, we have a better result. So if you want for further precision, you need to do for further iterations. So we are no more calculating further iterations. So that's our result. So if you see in the modified secant method, we converge to the original root at a very small iterations. So the computational cost was very small. So that's the advantage of modified secant method. So if you compare this with the original secant method, you will see that the modified secant method has a faster convergence rate. So the choice of proper value of delta is not automatic. If delta is too small, the method can be swamped by round of error caused by the subtractive cancellation in the denominator. So the delta cannot be too small or it cannot be too big, because if it's too big, it will cause an inefficient method and it will diverge. So we have to use the delta with the trial and error, because once the delta is not properly set, the method will not converge and it will diverge. So we have to be careful of the parameter delta whenever we are using the modified secant method. So in this lesson, we have learned about another open method, secant method, and also one of its variation, which is modified secant method. We have seen that both of these methods can be applied practically in a function, and we have seen that the modified secant method converges faster. So please try out the MATLAB code that I have attached with this lesson, and it incorporates both the secant method and the modified secant method. Please try out those codes and try to tweak the sum of the parameters inside the code and get the result. Use different forms of functions and get the results, and compare it with the other root finding equations like bracketing methods or Newton-Raphson method. So that's all for the secant method. In the next lesson, we will be learning about inverse quadratic interpolation method, and it's an extension of the secant method. So till then, thank you so much.